Okay, thank you. Thank you guys for coming to this session, and thank you for the introduction from Greg. Okay, I'm Yuhao Yang, and I'm a senior software engineer in the data analytics technology department of Intel. And today we are gonna be talking about building deep reinforcement learning with Apache Spark using analytics tool and Big DL. So a little bit about myself. I started with Spark about 4 years ago, and I was an active contributor to Spark ML Lab and contributed quite a few algorithms like FP growth and SVM, LDA in Spark ML Lab. And then I shifted my focus to the project, the deep learning project called Big DL, which is is a combination of deep learning and big data. So basically, we built this library called Big DL that can enable the big data users to train their deep learning models using their existing clusters. And now we are building this new project called Analytics Zoo. I will talk in more details in the coming slides. So this is the agenda for today. First, I will give an overview of the analytics tool, and then overview of reinforcement learning, and then I will bring two examples. First is DQN algorithms, and the second is distributed reinforce. And then I will talk about the future direction, the next steps for our project. So first, this new project called Analytics Zoo. Actually, it's just released open source in this June. And it's another analytics and AI platform for Apache Spark. And it's currently built upon Big DL. Big DL is, it has been open source since 2016. So it has been almost 2 years from now. And the project is becoming much more popular today, as right now it's a primary option for running a deep learning application on a CPU-based cluster. So the target for Big DL is to enable users to run deep learning applications with their existing big data cluster, leveraging both the hardware and the software architecture and the engineering resources. So here's the software stack. On the bottom, we leverage Apache Spark for the distributed execution and the fault tolerance. And on top of that, we built this Big DL library, which provides MKL acceleration. MKL stands for Mass Kernel Library, which is an native library on Intel architecture that can greatly improve the performance of matrix operations such as GEMM, so we can get a comparable performance on CPU for deep learning applications compared with GPU. And in Big DL, we further build a deep learning library from the bottom to the top. So we write the implementation for tensors, all the different layers, and the optimizer and the loss functions. And we further made some modification to the Spark curve to make it support the large model. Some mechanism like all-reduce are introduced to speed up the parameter synchronization in the distributed environment. And then on top of that, we built this analytics zoo. The reason we built it is that we found the user especially for industry customers, they didn't really ask for a deep learning library. They ask for an end-to-end solution. So they can just pick up the prototypes that you build and apply it to their scenarios, and hopefully can run the end-to-end POC in a few weeks. So that's why we built this zoo that contains collects our existing experience working with different customers in different industries. So first, Analytics Zoo contains some high-level pipeline APIs. First, we contains these N frames, which help users to especially Spark users, to build the deep learning models using Spark data frame and ML pipeline. We created an estimator and an transformer, which extends natively from Spark transformer and estimator, so people can directly assign their model to the estimator and run the training and inference with the estimator and the transformer pattern. We further build this Keras-style API to help users, especially Keras users, to quickly adapt to the Analytics Zoo API, so they can migrate their existing model or build a model that they would like. And autograde is a similar function in Keras and TensorFlow, basically supporting user to build custom layer and loss functions. And for transfer learning, we provide some extra API, so user can lock some layers and copy certain models from the layer or cut the last few layers from the model. And we further, in this Analytics Zoo, we provide some pre-built deep learning pipelines and models. Here are the 4 primary models that we support. Firstly is object detection. For object detection, we support SSD and faster RCN. We provide pre-trained models in both Scala and Python, so user can directly invoke the API and just run the inference with it. Similarly, for image classification, where we support nearly a dozen of different models, especially the popular models like VGG, Inception, ResNight. And for text classification and the recommendation, we provide the API that can help user to just adapt slightly according to their scenario and just try the deep learning models, such as wet and deep and the neural collaborative filtering for recommendation. And at least but not last, we provide some end-to-end reference use cases, which is built using BigDL and sometimes combined with Spark ML-like transformers. So reinforcement learning is the primary target that we are focusing today. And if you are interested in picking up some other deep learning libraries or applications, feel free to explore in the examples, such as some popular ones, such like anomaly detection and fraud detection. Okay, so next we are going to talk about reinforcement learning. I'm thinking maybe a lot of you have seen this picture if you are interested in reinforcement learning. Basically, in reinforcement learning, there are 2 parts of the word. One is agent, the other is the environment. During each time step, the agent will choose an action, and the environment will give the state and the reward to the agent. The examples for reinforcement learning applications, and it's becoming increasingly crazily popular in the last 2 or 3 years, even though reinforcement learning has been developed and discussed for almost 30 or 40 years. Some popular applications like play games, the popular Go, and interact with users. People are using it to build some recommendation and chatbot, and for driving and robotics or finance. So people are using deep neural network with reinforcement learning. In this graph, there are 2 square boxes, one on the left and the other on the right. On the left is the agent. So a primary reason that reinforcement learning is becoming really powerful nowadays is because that we can use the deep learning neural network to represent this agent, to help user to train a neural network that can simulate the agent's behavior, and so the agent in different state can choose a proper action for getting the maximum future rewards. So as you can see from the graph, the input for this action is the state from the environment. State pretty much is the feature in a neural network, or if you have any experience with any other model. And after the processing of this neural network, the DN model will output either the value for each action or the probability distribution for each of the action. And based on the different types of output of the model, they are called value-based solution and policy-based solution for reinforcement learning. And based on the output of this neural network, the agent will take the action and send it to the environment. So this kind of pattern can be applicable to many of the real-world problems. Like a chatbot, it gets the input from the user and it should send a proper message back. Or in the auto-driving case, the car sees the front of it and want to stop before the red light or avoid a passenger. We will use an example to help you to get more familiar with the different concepts in reinforcement learning. The first is the observation, which is the state. This is a game called Cat-Boo, and basically on the bottom there's a small cart, and on top of it there's a vertical pool. And the player will just play the left or right button to control the cart so the pool will stand straight. And in this case, the cart pool has 4 features to describe the state, which is listed in the first table, cart position and cart velocity. And you don't really need to care about the features, but just imagine that it as a feature of your input. And the actions are just 0 and 1, push the cart to left or right. And for this game, the reward is that the player should try to play as long as possible to hold the pole still. So every time step, you can think every many time steps, the reward will increase by 1. So that's the state and action and reward in this image. And now a few other concepts like policy and value function. So policy is just a behavior, it's just a function of states. So with the input of the function is a state and the output is just an action. So that's called policy. So don't think too much about it, just understand it from the word directly. And value function is an expected total reward from state S and action A. So in some state S, if you take an action, the Q pi SA represents the future total reward that you can get. And here in the equation, the lambda stands for a real value that's between 0 and 1. So that means the rewards that at the far end will have a less importance than the immediate reward. This is a simulation of the Markov process. We'll not talk in too much details today. But basically, this value function stands for how good is action A in state S. And as I mentioned, there are two branches of algorithms for reinforcement learning. First is value-based RL, where the neural network will output the value for each of the action. And another is policy-based. Output of the neural network is just the probability of each action. So that means if action A can take 90% probability and action B can take another 10%. That's what's the output of the policy-based reinforcement learning. We will not talk about model-based RL today. So deep reinforcement learning can be separated into those 4 different categories: value-based, policy-based, and as an intercept of it, there's another category called actor-critic, which is basically it uses two neural networks. One act as an actor, the other act as a critic. The two examples we are bringing today is DQN and the reinforce, one in the value-based and the other in the reinforce, in the policy-based. Okay, so now we go directly into the first example where we use DQN and to train a model based on Spark RDD. So for this neural network, the input, there are two kinds of choices. First is that we can use just the feature and the action as the input of this neural network, and then output the Q as the value for this action. Another choice is that we just use the state feature as the input of the neural network, and then output all the values for each of the action. And the popular choice is the right one, since that it means we can just run inference one time and get the result for all the action. If we use the pattern on the left, then for each of the action, we need to run the neural network multiple times, which is not, computing efficient. So for the Q value, an important thing to understand is that why we want to get this Q value. Q value stands for the value for each of the for an action in a state. And here, Q star SA means the maximum value that we can get. Once we get that Q star, we can, once we get all the Q star for each of the action, we can just use an argmax that choose the action with the max value. So it will be pretty straightforward. And usually people here will use set an epsilon parameter, which is another hyperparameter. So that, for example, if if epsilon is set to 0.1, that means on 90% scenarios, I will just choose the action that gives me the maximum reward. On the other 10% probability, I will just choose a random action. And the next is, the equation on the bottom just states that this calculation of the maximum value is actually an iterative process, so that the Q star value for this time step is actually can be derived from the Q star from the next state. That's still based on the equation of this, decreasing importance of the future reward, which is a simplified model based on Markov process. So once we get, this Q star, this iterative Q star definition, we can use value iteration algorithms to try to solve this Bellman equation, so that we can just update this Q value iteratively with the state, the Q value from the next. It would be like if the agent is standing in the current time step, and then it will take a step according to this, according to the argmax, choose an action that give me the maximum reward. Then I move a step forward. After that, I see all the value from this time step and just choose a maximum from that one. So that's the iterative process. So for deep Q learning, that's just similar to the process that I described. The agent will just choose an action according to the epsilon greedy policy. So most of the condition, it will choose an action that gives me the maximum reward. On some very few scenarios, very few percentage probability, I will just choose a random action. So just give the agent a chance to explore some other opportunity. And then I will just store those transition, the state, the action, the current reward, and the next state in the replay memory. And then I will just sample a mini batch of the transition from this saved memory. that will be my training data. After that, we'll just train an MSE between this Q network and the Q learning targets. In this next slide, I will just show you, this is actually a runnable code. So hopefully, by reading code, you can get more sense of how this algorithm runs. Usually in all the reinforcement learning, it's an iterative process. So the agent will have to play the games multiple times. Each episode, like in the count pool, represents one complete play, where user can play until that the pool falls. So for this many episodes, and in each of the episodes, the agent will play for maximum, here I defined as 500. So you can just thinking that the agent will just press 500 times of buttons to play the game. And in each of the time, the agent will just choose. Now, the parameter is actually initialized randomly. So the agent will just, the agent is just a neural network. It will choose an action based on the current weight and get an action that currently give it the maximum reward. After that, the environment will take a step. We'll just send that action to the environment, and the environment will send back the next state and the reward, and if the game has finished. Okay, and then the next state, then we'll just put this transition in the agent. And if we got enough of the records, we'll just call this agent.replay to start the training. And here's the procedure for the training. So we run them mini batch from all the memories that we already collected. This is called experience replay, so that my transition are actually sampled from the history for the last like 2,000 games. And that can break the correlation from each of the record and usually gives a better model. So the important, the critical routines is the target, how I update the target. So the target equals to the current reward and a gamma and multiplied by the maximum reward that the model predicts it should be in the next time step. And after this collection, we'll just transform all the training data into Spark RDD. And by calling feed, we can start the training. So this whole training process for the reinforcement learning happens iteratively. First, I play the game for a few times, and then I just train it. So it's likely, so maybe different from other deep learning applications. The play and we only train the model for a few iterations in each of the episode or time step, but we can train the neural network like millions of times during the whole play. And with the Analytics Zoo Kira style API, you can just define your model like this. This is a quite straightforward model. We got our input as the state size, which is 4 if we are using the cut pool example. And I keep adding some dense layers and using MSE as the loss criterion. And with this DQN, well, this super simplified DQN, we can get a result that at the start, the agent can, the vertical stands how many time, how long can the agent play the game. So at start, the agent will fail the game frequently at a low score, and gradually it will learn how to play the game. There are some bouncing because, well, on the right part, because we haven't really applied all the techniques like target delay and other techniques. And next we'll talk about this policy gradient, which, well, you can see in the result, the agent becomes much more stable than the reinforcement, than the DQN algorithm. As I mentioned earlier, in policy gradient, we just use a neural network to directly model the action probability. That means the output of the neural network will just be the probability of the action. And so we just tweak this parameter of this neural network so that the good action can be sampled more frequently than the bad ones. And I will bypass all the inference process, but this is actually how we update the parameter of the neural network. If you are interested in how I get this formula, one reference I would recommend is the David Silver's reinforcement learning classes. It's available on YouTube. And here, just intuitively, the reward is a scaling factor which dedicates how this probability should change in order to maximize the future expected reward. So for the reinforce, the algorithm is pretty straightforward. This is like a Markov process, so different from the DQN, which is actually based on time differential. Here in reinforce, we have to play the game end-to-end for several times before we can start the training. So in each of the time steps, we update parameters similarly to DQN. One outstanding issue is that since we need to play the game multi times before the training, the game playing part is taking too much resources, especially for the time. In each of the pillars, the red stands for the time for the game playing, and the blue part stands for the time for the training. So if we are using a single thread, just play the game and then train it, we soon will find that most of the time will be spent on the game playing. So that's why we try to distribute it with Spark. We build some classes that can help users to just create the distributed agents in a few lines. User can specify how many agents they want to create, and then each of the agent will just play the game by itself in the worker that it's on. So here with the distributed agents create, A.agent will just return an RDD of the agent. And after we have played the game, the RDD will be mapped to the sampled trajectories. Then we can just collect some statistics like the actions and rewards and the observations from each of the agents and summary all the transitions. So that's why we can save time by leveraging Spark distributed environment for the reinforcement for the distributed reinforcement training. So the reinforced algorithm works well, just similar, as the graph on the left. You need to play n games and collect all the samples, and then train and update model after that. Both of the game playing and the model training can be distributed by Spark, leveraging some utilities that we provided in Analytics 2. And the model for this policy gradient, quite similar to the previous one. The only difference is how we calculate that PG criterion, which is just still is quite simple. It's just a -1 multiplied by reward multiplied by y minus the probability. And after the distributed reinforce, we find that with a more, game playing, more experience, the result can be more stable. And we are still exploring other algorithms like we built this Flappy Bird demo with DQN. It can directly capture the image from the screen. So we are using a CNN-based network for this demo. And it's also available in the Analytics 2 if you are interested. We further built the discrete and continuous PPO algorithms, which is a state-of-the-art policy-based solution for the reinforcement learning. And the A2C algorithm is also another candidate that is in roadmap. Okay, looks like I have spent all the time, so let me know if there's some questions. And that's the link for the analytics zoo, and I want to thank my colleagues Sheng and Wang Yang for contributing to the notebooks. Thank you, guys. If you are interested in the notebook, they are available in the analytics zoo. The complete version is something like this.
So it looks like we are just about at time. We can probably get one question if somebody wants to come up to either of the mics here. Otherwise, I think our speaker will be available outside afterwards for discussion.
Yeah.
I have a question. Hi, it's a cool talk. So how is this analytics zoo different from Project Hydrogen that was like announced today? It's all about distributing TensorFlow or neural network code in Spark, right?
We can support importing TensorFlow and Keras and Caffe models into Big DL and then run it in analytics zoo.
Okay, so
Sorry, the question was that
is it similar to Project Hydrogen? It's basically trying to distribute TensorFlow code across Spark, like in Spark?
Well, the question is that can we
Are we distributing training, basically?
Yeah, sure.
Yeah.
Hi, I'm from the Big DL team as well. I think this question came up yesterday as well. Think of Analytics Zoo as almost an extension to Big DL, which is the only organic library built for Spark. Now, what I at least gathered from Project Hydrogen is it tries to make it easier to more organically, I guess, run TensorFlow, and I saw MXNet perhaps, to make it work, frameworks that were never designed for Spark to begin with. Yeah. So there's a lot more hooks that need to be put in play to make that work. But this is more of an extension to something that was a part of Spark. And also, what I gathered from Project Hydrogen was they are trying to make it more accelerator aware. Analytics Zoo is almost if you're familiar with TensorFlow model zoo, think of it as a big deal model zoo with the goodness of Keras in it. That's how I would put it. And obviously you can run it on CPU, hardware that you already have.